Hello students, welcome back to all. In this video, we will discuss about what is the valence bond theory and what are the properties of valence bond theory, right? So, in the last video, we discussed about whispered theory, right? So, this whispered theory is clearly explaining the shape of the molecule and how the bonds will form. All the things are explained by this whispered theory very clearly. And the repulsion of lone pair concept, repulsion of electrons, lone pair electrons as well as bond pair electrons is explained by the whispered theory very clearly, but it is a drawback that it didn't explain the strength of the bond. So to overcome these limitations, this valency bond theory is proposed in the year of 1954 by the scientist called Linus Pauling, and it is also one of the important theory to explain the chemical bond formation. So to describe the covalent bonding, a quantum mechanical model called valence bond theory. So the valence bond theory, in other terms we may call it as a quantum mechanical model. So it is developed by the scientist called Linus Pauling in the year of 1954. So what is the valence bond theory is describing about the bonds and how it explains the strength of the bonds. Let us see. So it explains about the covalent bond, which means we know how the covalent bonds will form. All those things we know, but it tells about that. See, when a covalent bond between two atoms is formed, see, take one atom and another atom, A and B. If the covalent bond is formed between the two atoms, when the two atoms approach each other closely and one atom overlaps its valence orbital containing unpaired electron with the other atom that contains unpaired electron in the opposite spin only. So the so formed paired electrons in the overlapping orbitals are attracted to the nuclei of both atoms. So this bonds the two atoms together. For example, what he told that, take hydrogen molecule. So in the last video we discussed how the hydrogen molecule will form. So here one hydrogen atom, take this hydrogen atom and take another hydrogen atom. It is containing one electron in the valence shell and it is also containing one electron in the valence shell. When these two hydrogen atoms comes close together, there exists a covalent bond between the two hydrogen atoms. But here one condition is there. The first hydrogen atom's last valence shell electron must contain the positive spin, and automatically the next hydrogen atoms must be in the opposite sign only. Then only there will be overlapping will takes place. Is it okay? In the formation of hydrogen molecule, the 1s orbital of hydrogen atom containing an unpaired electron overlaps the 1s orbital of the other hydrogen atom containing electron of opposite spin. If it is the positive, if it is clockwise, then it is anti-clockwise, plus then it must be minus spin. So the spin must be opposite sign. So the valency bond theory is explaining first the spin must be in opposite direction. So that is the first point. And now let us see the second point. See, in between the two orbitals there is a overlapping is there. Because of the overlapping there exists a sigma bond, right? See, if this overlapping is greater, then the strength of the bond should be greater. So the second point is, if the overlapping is greater, if the greater the overlapping of the orbitals that form the bond, then the bond will be strong. Strong will be the bond. So the valency bond theory is explaining the first point about the spin and the second point about the strength of the bond, which means if the overlapping is greater, then the bond formed will also be greater, which means stronger. So this gives a directional character to the bond when the other than s orbitals are involved. So I will explain this point with example. You have to remember that if the overlapping is greater, then the bond will be stronger. So now let us see the next point. So the third point is that each bonded atom maintains its own atomic orbitals. For example, take two hydrogen atoms. So each bonded atom maintains its own atomic orbitals. But the electron pair in the overlapping orbital is shared between the two orbitals equally, which means the electron pair in the overlapping orbital is shared by both the atoms involved in the overlapping. That is quite common, you know. The overlapping pair is shared between the two atoms equally, which means the overlapping takes place between the two atoms is equal, which means the two atoms will equally involving in the overlapping. If you see the fourth point, if any two atoms, in between the two atoms there will be multiple bonds. If suppose there exists triple bond or double bond like this, multiple bonds, then we have to know it first. The first bond formed in between the two atoms, overlapping of orbitals is along the internuclear axis. So what is the internuclear axis? Which means it is an imaginary line. It is, for example, take A and B. So this is A and this is B. So if an imaginary straight line is drawn that connects with the nuclei of atoms bonded each other, so this is called internuclear axis. So when in between the two atoms there will be multiple bonds are there, the first bond must be formed by the overlapping of orbitals of along the internuclear axis, which means the bond which is formed along the internuclear axis is called sigma bond. So very important. The sigma bond forms first and it is the stronger bond. After formation of sigma bond, other bonds are formed. So the second bond and third bond, these bonds are formed by the overlapping of lateral overlapping or side-wise side overlapping. So this is called pi bond. So pi bond is weaker bond, sigma bond is stronger bond. So difference between pi bond and sigma bond, if you see, the pi bond will always comes first. In between the two atoms, bonded atoms, the first sigma bond will form, then only the pi bond will exist. Without sigma bond, pi bond doesn't exist. That is the first point. And second point is that in sigma bond there is a end-on end overlapping. End-on end means along the internuclear axis. Whereas in pi bond there is a side-wise side overlapping, which means lateral overlapping will take place in the pi bond. And sigma bond is stronger bond, whereas pi bond is the weaker bond. So we should concentrate on the sigma bond and pi bond. So I will explain this sigma bond and pi bond with some examples. So for example, take Cl2 molecule. So consider Cl2 molecule, which means in between the two chlorine atoms there is a single covalent bond. How this covalent bond will form? Let us see. So if you observe here, the chlorine atom contains 7 17 electrons in the its electronic configuration is 17. So configuration is 1s2, 2s2, 2p6, 3s2, 3p5 here. So if you observe here in the outermost shell, it contains 7 electron. To get the octet configuration, it requires only 1 electron, right? So if you observe here, 3p5 means here, if you write the 3p orbital, so this is 3px, 3py, 3pz. So 3p5 means 1, 2, 3, 4, 5. So if you see here, in the 3pz orbital, there is an unpaired electron. This unpaired electron will only involve in the bond formation, right? So this 3pz orbital is overlapping. In this chlorine atom, there is a 3pz orbital contains unpaired electron. In the second chlorine atom also, there is a 3pz orbital, it contains unpaired electron. So this is 3pz orbital. So this is chlorine atom, it contains one unpaired electron. It is overlapping with the other chlorine atoms. It is opposite spin. This is also 3pz orbital. So when these two atoms are overlapping along the internuclear axis. So if you see here, this is called along the internuclear axis. Here there exists a bond, and that bond is called sigma bond, because here in both the chlorine atoms there is a end-on end overlapping is there. So that is why here there exists a sigma bond between the two chlorine atoms. So chlorine atoms containing single bond, and that single bond is nothing but sigma bond. Is it clear? So like this the sigma bond will exist in between the atoms. And now let us see one more example. So for example, let us see the formation of N2 molecule. So here if you see the nitrogen atomic number 7 containing 1s2, 2s2, 2p3. So 2p3 means here 2px1, 2py1 and 2pz1, right? So nitrogen atom overlaps px orbital of the other nitrogen atom. For example, take another nitrogen atom, it is also having the same structure, same configuration, 1s2, 2s2, 2p3. 2p3 means here also there are 3 orbitals, 2px1, 2py1, 2pz1. So 2py1 and 2pz1. So take the nitrogen atom. So this is px, py and pz. Take another nitrogen atom. So here in this case, this is nitrogen atom 1 and 2. So px, this is px, 2px, 2pz and 2py. Each atom containing one unpaired electron. So here also 1, 1, 1. So 2px, 2py, 2pz. So when the overlapping will takes place between the two nitrogen atoms, so here the 2px orbital will overlapping with the other 2px orbital of the nitrogen atom. So this is 2py, 2py orbitals. So this is 2pz and 2pz. So if you observe here, so this is 2px, first nitrogen atom, second nitrogen atom. So this is 2px, these are 2py, these are 2pz. So if you observe here, in between the two nitrogen atoms, there is a bond along the internuclear axis. So that is nothing but the sigma bond will form here. So when you observe here, in the 2pz orbital, there is a one unpaired electron, and the 2pz orbital, another one paired electron. So in between the 2py, there is a lateral overlapping is there. So here, so 2px orbitals, there is a sigma bond, and in between the 2py orbitals, there is a pi bond, because here lateral overlapping is takes place. So if you observe here, in between the 2pz orbitals, so this is 2pz, this is 2pz, 2pz orbital, 2pz orbital. So in between 2pz orbital, there exists a pi bond. So when you observe here, in between the nitrogen atom, there exists a triple bond. So one bond is sigma bond, and the remaining two bonds are pi bonds. And these two pi bonds will always depend on the sigma bond, which means first the sigma bond will exist, then after there will be possibility to form pi bonds. So here the 2px bond is stronger bond. The remaining two are weaker bonds. So like this, the nitrogen molecule will form. So here when we observe here, the sigma bond is formed between the 2px orbitals along the internuclear axis. So this is called end-on end overlapping. So when you observe here, the pi bond will form between the 2py and 2pz orbitals. This is sidewise overlapping. So this is lateral overlapping. So like this, in between the nitrogen molecule, there exists triple bond, and one bond is sigma bond and two are pi bonds. So this is the formation of nitrogen molecule. Now let us see one more example. So formation of oxygen molecule. Oxygen molecule means O double bond O. In between the two oxygen atoms, there exists a double bond. Now let us see how the double bond will form between the two oxygen atoms, right? So we know oxygen atomic number 8 configuration is 1s2, 2s2, 2p4. So 2p4 means 1, 2, 3, 4, which means in the 2px there are 2 electrons, 2py 1 electron, and 2pz 1 electron, which means here only 2 orbitals having unpaired electrons, 2py and 2pz. So if you take the another oxygen atom, here also 2p4 means there exist 2 unpaired electrons in 2py and 2pz. So here only the 2py 2pz orbital will win the bond formation. So if you draw the structure, so this is 2py, sorry 2pz, this is 2py orbital. So here also this is 2py orbital and this is 2pz orbital. So here one unpaired electron, here also one unpaired electron in each case. So this is opposite spin. When these two orbitals are overlapping, then so in between so this is 2py orbitals. So these are 2pz orbitals, right? So here in between the 2py orbital, there exists a sigma bond, because this is along the internuclear axis, this will form. Here when we observe the 2pz, there is a lateral overlapping. So here pi bond will form. So like this, in the oxygen molecule, one sigma bond is formed between the 2py orbitals of oxygen atoms, and one pi bond is formed between the 2pz orbitals of the oxygen atom. Here in this case the 2px orbital didn't have unpaired electrons, so that is why it is not involved in the bond formation, right? Only 2py and 2pz orbitals are participate in the bond formation. Here when we observe here this sigma bond, so this is sigma bond, it is along the internuclear axis, it forms along the internuclear axis, whereas the pi bond is lateral overlapping, which means this pi bond will always perpendicular to the internuclear axis. So you have to remember one point, the pi bond is always perpendicular to the internuclear axis, but the sigma bond always forms along the internuclear axis. So like this the oxygen molecule will form. In oxygen molecule there exists a double bond, one is sigma bond and another one is pi bond. Sigma bond is stronger when compared to pi bond, and here the sigma bond is formed between the 2py orbitals of the oxygen atoms, whereas the pi bond is between the 2pz orbital of the oxygen atoms. So this is the formation of oxygen molecule. Now let us see one more example. So now let us see the formation of beryllium chloride. Already we discussed in between the beryllium chloride there exist two covalent bonds. So one bond is between the chlorine and beryllium and other bond is between the beryllium and chlorine. So like this beryllium chloride there are two covalent bonds, right? So if you observe here the beryllium is 4 1s2 2s2. So if you observe here the beryllium having no unpaired electrons, right? So it is expected to not to form covalent bonds, but the beryllium will form two covalent bonds with the two chlorine atoms. The beryllium chloride molecule will exist in practically. So how it is possible? See, when any atom is undergoing bond formation means it must contain the unpaired electrons. Otherwise it may not overlap or participate in the bond formation. But here in this case, in case of beryllium, it contains no unpaired electrons because the 2s2 orbitals contains 2 electrons itself. Then how it will undergo bond formation? Practically there exists a beryllium chloride molecule, which means here to explain this we have to understand one more concept here, and we will study this concept in the topic atomic structure. So in the atom, so these are the inner shells. The electrons are revolving around the nucleus in the shells, right? So the atom contains number of shells, right? So sometimes the electrons will jump from ground state to higher energy shell and it comes back. So which means here the excitation will be possible. We will discuss this excitation concept in the atomic structure topic. So the electron sometimes is excited from ground state. Ground state means lower energy. Excited state means higher energy. So when the electron is excited from ground state to excited state. So this concept is explained here. See, the beryllium contains configuration 1s2 2s2. So this is ground state electronic configuration. But the excited state electronic configuration is 1s2 2s1 2px1. Why? See here 2s2 means it contains the 2p0, which means one electron is excited from 2s orbital to 2p orbital. Then the excited state electronic configuration of beryllium will be 1s2 2s1 2px1. So now the beryllium will have two unpaired electrons. So it is easy to participate in the bond formation now, which means because of taking the ground state electronic configuration, the formation of beryllium chloride is not explained. So to explain this concept, an excited state suggested for the beryllium. So here in the excited state, one electron from 2s orbital is excited from 2s to 2p orbital. So the excited state configuration is 1s2, 2s1, 2px1. So now it contains two unpaired electrons. So the beryllium will form two bonds with the two chlorine atoms. So now let us see how the beryllium will form two bonds. So beryllium, its excited state configuration is 1s2, 2s1, 2px1. So when we see here in the excited state, it contains two electrons. So 1, 2. If you see the chlorine atom, so we know chlorine already contains 17 electrons. So 1s2, 2s2, 2p6, 3s2, 3p5. So when we observe here in the 3p5, it contains 7 electrons. It requires one more electron to get octet configuration. We know it very well. So when you observe here, 3pz means 1, 2, 3, 4, 5, which means here the 3px2, 3py2, 3pz1. Only the 3pz orbital contains unpaired electrons. So the chlorine atoms, the 3pz unpaired orbital will participate in the bond formation. But here in the beryllium atom, two unpaired electrons are there, 2s1 and 2px1. So if you see here, this is 2x1. If you see here, this is 2px1 orbital. And chlorine atoms, 3pz orbital will participate in the bond formation. So this is chlorine atoms 3pz orbital. So when we observe here, this is 2s1 orbital of beryllium and 3pz orbital of chlorine. And this is 2px orbital of beryllium and 3pz orbital of chlorine. So in between there are two covalent bonds are formed. See, when you observe here, two covalent bonds will form. So these two covalent bonds must be sigma bonds, because here there is a end-on end overlapping is there. The two bonds are formed along the internuclear axis. The overlapping will be along the internuclear axis. So that is why in beryllium chloride there exist two sigma bonds. Right. So now it is clear. And here the orbitals are overlapping are different in two cases. So see here, in between the beryllium chloride there exists 180-degree bond angle, and the both bonds are same because the two bonds are formed, two sigma bonds are having same strength. There are two single covalent bonds are formed, and the two covalent bonds are must be the sigma bonds, and both are having the same strength. So here my question is, here in the bond formation, in the first case there are two different orbitals because the first sigma bond is formed between the 2s orbital of beryllium atom and 3pz orbital of chlorine atom. And the second sigma bond is formed between the 2px orbital of beryllium atom and 3pz orbital of chlorine atom. Here the orbitals involved in the bond formation are different. Then how the two bonds are having the same strength? Is it clear? When we observe here, the beryllium will form two sigma bonds, and two sigma bonds must containing the same strength, equal strength. But when we observe here, the two sigma bonds are not formed between the two similar orbitals. Two orbitals are not same because the 2s orbital is forming sigma bond with the 3pz orbital in first case. In the second case, 2px orbital is forming bond with the 3pz orbital. The orbitals involving in the bond formation are different. Then how the bond strength is same? So, to explain this discrepancies like this concept, there is a new phenomenon which is very important called hybridization. So to explain this concept, there is a hybridization concept is proposed by the scientist called Linus Pauling. Is it clear? So who introduced hybridization means that is nothing but Linus Pauling. Why he introduced means to explain the dissimilar phenomenon of some elements, because if you take in case of beryllium chloride, it is not explained without hybridization. So here two bonds are forming having the similar strength, but here the orbitals involving are different. Then how it is possible? How the beryllium chloride molecule will exist in practical? So to explain this concept, the hybridization is proposed by the scientist called Linus Pauling. Now let us see what is the hybridization. So here, what is hybridization? It is a phenomenon of intermixing, very important, intermixing of atomic orbitals of almost equal energy which are present in the outermost shell of the atom, and the reshuffling or redistribution into the same number of orbitals but equal properties like energy and shape. See, if you see in case of beryllium, the beryllium atom will exist two different orbitals. One is 2s orbital and another one is 2px orbital. The two orbitals are different but are having different shape, because s orbital is spherical shape, p orbital is dumbbell shape. So almost they are having equal energy, which means the 2s and 2p both are present in the same main shell, but when you come to that structure shape, s orbital having spherical shape whereas p orbital having dumbbell shape. When you compare their shapes, the structure is different, but when you see, the two orbitals will present in the same main shell. So because of which means they are having they are having almost equal energy. Such type of orbitals are intermixing which are present in the outermost shell of the atom. By intermixing those orbitals, reshuffling or redistribution into the same number of orbitals, and we will get the new orbitals, and that new orbitals having equal energy and equal shape. That phenomenon is called hybridization, which means if you add the two orbitals, we get the two new sp hybrid orbitals. If you had three orbitals, we will get the three new hybrid orbitals. Hybrid orbitals means which are having equal shape and equal energy. By intermixing two orbitals, we will get the two new hybrid orbitals. The new hybrid orbitals always having equal energy and equal shape. So this phenomenon is called hybridization, which is explained by the scientist called Linus Pauling. So by this concept, we will explain so many examples. Is it okay? Let us see one example. For example, take the same beryllium chloride molecule. How the beryllium chloride molecule will form? For example, we know beryllium's excited state configuration is 1s2, 2s1 and 2px1. So here 2s1, 2px1 both are having unpaired electrons and they are present in the outermost shell, and both are having almost equal energy because the 2s and 2p will present in the same main shell, that is L shell, right? So the 2s orbital and 2p orbital will have almost equal energy, but the shapes are different, of course. So by intermixing these orbitals, s orbital and p orbital, we will get two new hybrid orbitals. So the name is sp hybrid orbitals. These are called hybrid orbitals. So here in this case we are intermixing two orbitals and we will get two sp hybrid orbitals, and these two sp hybrid orbitals having equal shape and energy. So if you see here, this is beryllium atom. So this is the first sp hybrid orbital, this is second sp hybrid orbital. Both are having 2 electrons. So this is sp hybrid orbital, this is also sp hybrid orbitals. Now the chlorine atoms 3pz orbital will intermix. So this is 3pz orbital and this is also 3pz orbital, like this. So this is 3pz orbital, 3pz orbital of chlorine atom. So now here by intermixing here the head-on and overlapping, the overlapping along the internuclear axis which takes place, there exist two sigma bonds. Is it okay? And the two sigma bonds are formed between the sp hybrid orbital of beryllium atom and 3pz orbital of the chlorine atom. So now the two orbitals having equal strength. So in the earlier, if it is not undergo hybridization, so one sigma bond is formed between the 2s orbital and 3pz orbital, and second orbital will formed between the 2px orbital and 3pz orbital. So but now the two sigma bonds are formed between the sp and 3pz orbitals. So now by explaining this hybridization concept, the beryllium chloride formation will be explained clearly. So this is the formation of beryllium chloride. So now the two bonds are having same strength because there are two equal orbitals are involving in the bond formation, sp sp, 3pz 3pz. So two bonds are having equal strength and the bond angle is 180 degree. So this is the formation of beryllium chloride by the concept of hybridization. And one more example, let us see the formation of BF3. For example, take the BF3. So already we discussed how the BF3 will form and what is the structure BF3. So like this, the BF3 molecule will be formed having trigonal planar, right, having three bonds, three covalent bonds, three bond pairs, 1 2 3. So we know it very well. See, if you observe here, take the boron, it is containing 1s2, 2s2, 2p, x1, right. So this is the ground state electronic configuration. In the ground state, it contains only one unpaired electron. Then how it is formed three bonds with the three fluorine atoms? Because the unpaired electrons will only involve in the bond formation. So when you observe here, only one unpaired electron is there. So that is why the excited state configuration is also required for the boron. So what happened here? One electron is excited from 2s orbital to 2p orbital. Then the configuration will be 1s2, 2s1, 2px1, 2py1. Because here the 2px1 means there is 2py0, 2pz0. So that is why here one electron will be excited from 2s orbital to 2py orbital. So now the excited state configuration is 1s2, 2s1, 2px1, 2py1. So if you see in the excited state, in the outermost shell, it contains 3 unpaired electrons. So now the 3 unpaired electrons will form 3 bonds, 3 covalent bonds with the 3 fluorine atoms. So here also there are 3 types of different orbitals. So s orbital, 2px orbital and 2py orbital. Again, the 3 orbitals are not equal, which means the 3 bonds are formed between the boron and fluorine are not having the same strength. Again, this is also explained by the hybridization concept. How the hybridization will take place here? Here the 2s orbital and 2px orbital and 2py orbital, there are total number of 3 orbitals will intermix. So the intermixing of 3 orbitals will take place and we get 3 sp2 hybrid orbitals. Why sp2 means one s orbital is there and 2 p orbitals are there. So that is why sp2, 1s and p2. So total number of 3 new hybrid orbitals we get by intermixing the 3. So now the boron will have 3 new hybrid orbitals and the name is 3sp2 and having equal energy and shape. Let us see the formation of BF3. So the boron will have 3, 1, 2, having 3 orbitals. So this is sp2, sp2, sp2. These 3 are sp2 hybrid orbitals, each having 1 unpaired electron in each case. So if you see the fluorine atom, it is 1s2, 2s2, 2p5. So 2p5 means 2, 3, 4, 5, which means 2px2, 2py2, 2pz1, which means in the fluorine atom the 2pz orbital will intermix, will undergo bond formation. So here this is 2pz orbital of the fluorine atom. So this is 2pz orbital and this is 2pz orbital. So when you observe here, in between the boron and fluorine, there exist 3 sigma bonds. Because here head-on and overlapping will take place, so here the 3 sigma bonds will be formed. See, in case of hybridization, you have to remember one point. The bonds which are formed in the hybridization are all sigma bonds only. There is no possibility to form the pi bonds. In case of hybridization, there will be sigma bonds only. Is it okay? So here the 3 sigma bonds will form between the sp2 hybrid orbital of boron atom and 2pz orbital of fluorine atom, and having the bond angle is 120 degree. We know it well. And the structure is also trigonal planar. So like this the BF3 will form. And now let us see one more example. So formation of NH3 molecule, ammonia. So we know that ammonia will form 3 sigma bonds, 3 NH bonds, and all are having the same strength, and bond angle is 107 degree 48 minute. We discussed in the last class, right? So here take the nitrogen atom. So atomic number 7 configuration 1s2, 2s2, 2p3. So in the 2p3, 2px1, 2py1, 2pz1, right? here the 3 hydrogen atom is overlapping 1s orbital. Hydrogen means only 1s orbital. If the 3 nitrogen atoms, 3 hydrogen atoms are overlapping 1s orbital on 3 orbital of nitrogen atom. So we get 3 sigma bonds between p orbital and s orbital. See, because this is nitrogen, it is having 3 bonds with the 3 hydrogen atoms, right? The 3 sigma bonds between the 3 hydrogen atoms. So if it is formed like this, of course there will be lone pair on the nitrogen atom. Then there is a possibility to having the bond angle should be 90 degree, because here there are 3 bonds are having same strength. Then it should be the bond angle 90 degree. But practically the bond angle of NH3 is 107 degree 48 minute. How it possible? Again, to explain this property, the nitrogen atom is said to be undergo hybridization. So now the nitrogen atoms containing the configuration like this. So the nitrogen atom is undergo hybridization by intermixing of 1 2s and 2px and 2py and 2pz orbitals. So totally we get sp3 hybridization. Why sp3 hybridization means 1 s orbital and 3 p orbitals. So total number of 4 orbitals will intermix and we get total number of 4 new hybrid orbitals. And the 4 sp3 hybrid orbitals are having equal energy and shape. So in the ammonia, nitrogen molecule will undergo sp3 hybridization, right? So here the total number of 2, 3, 4, 5. Total number of 5 electrons are there in 4 sp3 hybrid orbitals, which means in 4 sp3 hybrid orbitals, one orbital having one electron pair. The remaining 3 orbitals having unpaired electron, which means single electron in each case. So like this, there are total number of 5 orbitals are there. So take the nitrogen atom. So like this, and it is intermixing with the 1s orbital of hydrogen atom. So like this, there exist 3 sigma bonds between the sp3 hybrid orbital of nitrogen atom and s orbital of hydrogen atom. So this is the formation of nitrogen ammonia molecule. But here actually the bond angle should be 109 degree 28 minute. Because of the presenting of lone pair bond pair repulsion is more, due to the repulsive force the bond angle is distorted from 109 degree 28 minute to 107 degree 48 minutes. So this is the bond angle of ammonia. So like this the ammonia molecule will form. Next, let us see one more example. So formation of water molecule. We know oxygen having 2 lone pairs and forms 2 single covalent bonds with the 2 hydrogen atoms and having the shape V shape and bond angle is 104 degree, right? 31 minute. So we know it very well. But here see, if the oxygen forming, see oxygen atomic number 8. So 1s2, 2s2, 2p4, right? So 2p4 means 2px, 2py, 2pz and 2px2, 2px2, 2py1, and 2pz1. So here only 2py orbital and 2pz orbital will undergo bond formation. Therefore, there is a possibility to form 2 sigma bonds between the S and P due to the overlapping of S orbital of hydrogen atoms and P orbital of the oxygen atom, right? So this is the one bond and second bond. There are 2 sigma bonds between the S and P orbital of hydrogen atom and oxygen atom respectively. If it is formed in that way, then the bond angle between the hydrogen and oxygen molecule should be 90 degree. But we are observing the bond angle in the water molecule is 104 degree 31 minute. Again, to explain this concept, the oxygen will undergo sp3 hybridization. Which means the oxygen molecule will undergo 1 2s orbital and 3 2p orbitals. Will undergo sp3 hybridization. We will get 4 sp3 new hybrid orbitals. Let us see how the bond formation will be there. See, the oxygen 1s2, 2s2, 2px2, 2py1 and 2pz1. So now 1 2s orbital plus 2p orbital, 2px, 2py plus 2pz. So 1, 2, 3, 4. Total number of 4 orbitals will intermix, undergo hybridization, and we will get 4 sp3 hybrid orbitals. So here in this case, in 2s there are 2 electrons, 2px also 2 electrons, single electron, single electron. So total number of 6 electrons are distributed among the 4 sp3 hybrid orbitals, which means 2 sp3 hybrid orbitals contains 2 electrons in each case, and the remaining 2 sp3 orbitals containing 1 unpaired electron in each case. So for example, take the oxygen atom. So it is containing 2 lone pairs, and this is 1 sp3 hybrid orbital and this is another sp3 hybrid orbital. If it is overlapping with the s orbital of the oxygen atom, so there will be 2 sigma bonds between the sp3 hybrid orbital of oxygen atom and s orbital of the hydrogen atom, and the bond angle is 104 degree 31 minute. So like this, the oxygen atom will undergo sp3 hybridization. So this is the formation of water molecule. See, again there are number of compounds are there. For example, methane is there, CH4, and C2H4 is there, C2H2, and so on. Many compounds are there, and we will discuss these compounds and their hybridization structures in the next video.